All right. Neutralization reactions. Oh, 1 second. That's backwards. Justice, do me a favor.
Mm-hmm.
Grab that eyeglasses on the bottom where it says eyeglasses at the window. Drag it up.
This?
Yeah. Should be a grab and drag.
Where is it? Oh, there we go.
Press mirror on the bottom right. There you go. Hello! Let's get this party started. All right. I can't see what they're saying. I thought it was saying.
That's cool.
All right.
Oh, I think I know this from summer.
All right, let's try this one. What volume of hydrochloric acid is needed to neutralize 25 milliliters of NaOH? Huh. I almost want to do this. Okay, all right. Let's do this. Let's do it this way. What volume of 0.1 molar hydrochloric acid is needed to neutralize NaOH? All right, so I've got hydrochloric acid, HCl, and I also have NaOH. Right? According to precipitation rules, does NaOH break up?
Yeah.
Oh, I'm sorry. This is NaOH, sodium hydroxide.
Yes.
The answer is yes. I think that I think the rule states exactly that most hydroxides don't break up, except for KOH and NaOH are notable exceptions to that rule. So this thing breaks up. NaOH ions. Got it? You got some sodium ions in there. You got some hydroxide ions in there. Does HCl break up?
No.
No, it does not. It is an acid. And in the rules, it doesn't say it breaks up.
Yeah.
But I'll tell you what happens, okay? What ends up happening is this OH is such a strong base that it literally rips off this H. It's like, I need it. Boom. Give it to me. So, it actually does break up. You see that? Because the base of the OH is so strong of a base that it reacts with the acid and it rips off the H. And it happens in a reaction that you're very familiar with. Well, what can be created? Okay, well we have H, let's see, how would I want to do this? Okay, H plus Cl minus plus Na plus OH minus will give me, so this is the stuff I'm having go into the thing, right? And what will that give me? That will give me H2O, liquid, right? Plus, what else? Na what?
NaOH.
Nope. NaOH broke down.
Oh.
And I stole the OH from, I stole the OH to make H2O. I can't see what they're saying. What are they saying?
Salt.
Salt, exactly. NaCl.
NaCl.
But NaCl, does that break up into inside of a solution?
Yes.
Yes, because anything with sodium in it breaks down.
Yeah.
So NaCl. I wrote those separately because those don't actually stay together in a reaction. They break back down. Salt dissolves in water. That's all I'm saying. Right? So I can cancel out the Cl's and the NAs because those are what we call spectator ions. They didn't actually do anything.
Okay.
Right? And so here's the reaction that actually took place. Something that you are very familiar with. Of course, a hydrogen ion combined with a hydroxide ion makes dihydrogen oxide. Or, well, I don't even know if that's not the right name. It makes monohydrogen hydroxide, also known as water.
Really?
I don't know. I don't know how to say this scientifically. I just call it water. Like, I don't know the chemistry name for this. The nomenclature, as we would call it. Anyway, whatever. Does that make sense? Am I confusing anybody? All right. So let's play this game. You ready? What did they say? They said 25 milliliters of NaOH. Oh, NaOH. And obviously what I'm going to want to do is convert that to moles of something. Well, in order to convert to moles, first of all, it's 25 milliliters. I'm going to make that 0.025 liters. Is that all right with everybody?
Yes.
Do you understand why I did that?
Yeah.
It's because when I'm dealing with molarity, in fact, almost when I'm dealing with all of chemistry, I like dealing with liters. Gas is dealt with liters, when molarity is in liters, so I'm going to convert it straight out to liters, so that way I don't have to do a middle conversion, if that's all right. I'm going to use the molarity to convert that into moles. I know that there are 0.350 moles per liter of NaOH. Got it? Now, I have a question for you, and this is where you guys might want to pay attention because this might be a little bit different from what I usually do. Is for every one NaOH, how many hydroxide ions do I get?
Two.
Nope. I get one hydroxide and one sodium. One NaOH gives me one hydroxide and one sodium. Got it? So is it right with you if I just change this to an OH minus? And what I'm saying here is however many moles of NaOH is the same number of moles of OH minus that I have, right? That I'm starting off with. Is that all right with you? I didn't confuse anybody, did I? So what I'm doing is, just as you said that you're good with the stoichiometry game, right?
I'm not good, but I understand.
Well, I haven't played the stoichiometry game yet. We're just at the starting line. And to get to the starting line, you need to start off with moles of the stuff that you have. Got it? Now we play the stoichiometry game. We want to convert the OH to hydrogen. And we want to see how much hydrogen is required. So, check this out. I want to go from moles of OH to moles of hydrogen. Here's the stoichiometry step. You ready? There's going to be a number here and a number here. What numbers go there? Dude, if you want, you can stand over here on the inside. Feel like you're in a cage.
Okay.
Does anyone know what numbers go here and here? I'll give you a hint. You have to look.
Molarity.
No, you have to look at the balanced equation to find what those numbers are.
Oh, 1 and 1.
Good. 1 and 1. Where's the balance equation? It's right there. There's a 1 here, a 1 here, and a 1 there. Done.
Yeah.
Stoichiometry. Done. All right. So let's see. Now I have moles of hydrogen ion. And I think that the question was, they wanted me to convert that to liters.
Oh, Cameron asked, how do we know that OH is a negative ion?
Oh. OH is a negative ion because O has a -2 charge on it usually, and H usually has a +1 charge on it. So when you have an O and an H, it's -1. Does that make sense?
Yeah, he said okay.
Okay. All right. Last step. All I need to do is I need to convert this moles to liters. Okay? So I can use the molarity, which they gave me in the problem. You guys are asking me, well, where did you get this number? This was given to me in the problem. Where did I get this number to start off with? That was given to me in the problem. Where did I get this?
From the balance equation.
That's from the balance equation. This is our stoichiometry step. The last one is the molarity. And then what I'm going to do is I'm going to divide it by 0.1 moles for every liter of H+. Where did I get 0.1? Because the problem told me that I had 0.1 molarity hydrochloric acid. So I put 0.1 molarity hydrochloric acid. Why did I divide by 0.1 as opposed to multiply by 0.1?
Because you're trying to find how much it is in liters.
Because I'm trying to find how many liters, but also I wanted to cancel out the moles. See, the reason why I set this all up is because this is all of my steps, just going right through. You start off with a volume. You convert that volume to moles using the molarity. Now that we have the moles, we can play our stoichiometry game. We play our stoichiometry game. It's really easy. It's one line right there. Then you have moles as your answer. Am I done? No, because they asked for liters at the answer, so you use the molarity again to convert it back to liters. Literally, you multiply all this stuff through, and you'll get your answer. Someone, Nanea, posted a question. What is that?
Is this an assignment problem?
No, this is an example problem. But I believe that a problem similar to this is on your homework. Got it? All right. If I were to plug in the answers, it would be 8.75 times 10 to the negative 2 liters. Also known as, I think, 87.5 milliliters.
She asked if it was today's one.
I'm not sure if this is today's one. This is section 4.8, I think. So it could be. I'm not sure which one I assigned.
Yeah. Oh, shoot.
Don't worry about it. All right. Hey, I want to show you guys something because I want to show you actually how we do it. Here, get up real quick. Dude, you're just attached everywhere.
I know, right?
All right.
Too many cords.
I'm going to close this out, and I'm going to show you my computer screen. Hopefully this works. So here's how we would actually do this in a chemistry lab. And sadly, I wish I could have done this lab with you guys a couple weeks ago, but I don't have the equipment. And Celeste never brought in her burette.
Oh.
So, nah, that's cool. I'm just giving you a hard time. All right. Anyway, I'll show you guys how we do this in a chemistry lab because I think it's really interesting. As soon as my computer decides that it wants to share my screen with you. Let me know when you guys can see my computer screen. You guys got it? All right, here we go. Let's see. You can just hang out here or stand right up and look at my computer screen. Anyway, here's what we do. We do this thing called, oh, perfect. All right. We do this thing called titration. And what it is there is a, there's a Erlenmeyer flask down here, right? And that thing's spinning around. I don't know if you guys can see it on the computer screen at home. What do you guys see? All right. It's all right.
Oh, yeah.
In fact, if you guys want to do it here, try going to this website.
No, you can see it.
It might ask you, but here, you guys can just watch my computer screen for now. Anyway, here's how we set it up in the chemistry lab, and I would actually have you guys do this because it takes a lot of practice, but it's interesting. It's really fun. One of the things we do is we say, okay, let's fill up our burette with a base. Let's fill it up with, no, let's put the acid inside there, okay? And so the burette is filled with hydrochloric acid, got it? And So this thing right here, this tube, is filled up with hydrochloric acid. And this flask down here is filled up with sodium hydroxide, NaOH. Got it? And then what I'm going to do is I'm going to put an indicator in. And what the indicator does is it fills up, or it tells me exactly how much, or like when they're balanced. Because as I add, if I have NaOH, and as I add more hydrochloric acid, what will happen?
Becomes clearer.
Well, no, but what will happen if I have an acid and I add a base to it? What happens?
It causes precipitation.
No. Well, what happens is, all right, think of this. An acid, if you guys think back to like 7th grade science, when we talked about pH scale, okay? An acid has a really high number on the pH scale, right? 7, or like middle is 7, but an acid has like 14.
Yeah.
And do I have that right? I think I might. I hope that's not backwards. Anyway, it's on one end of the pH scale, right? A base is on the other end. So if an acid is really high number, then a base is really low number. Celeste, sorry, one question real quick. Sorry, acids are high pH, right?
No.
Acids are low pH. Okay, I'm sorry, I got that backwards. Acids are really low numbers for pH. Bases are really high numbers for pH. But if I mix an acid and a base together, what will happen?
It would come to a medium.
There we go. Exactly. It comes to a middle understanding point, like a neutral center. Got it? So what this bromothymol blue is doing is, actually, I'm going to switch this up. I'm going to put a base in
It's
here.
coming to a medium.
What's happening here is this. What I'm going to do is I'm going to put base inside here. Okay, HCl, NaOH. All right. What's happening here is I'm going to use this thing called phenolphthalein, which is a really cool solution. And as I add this thing to here, if it's right now inside of here, there's straight up pure hydrochloric acid. Okay, so when this thing, what is in here? Is a high pH or low pH? It's hydrochloric acid. It's an acid.
So it's low.
It's like the acid that will melt your face.
So it's a low.
It's very low. Okay, as soon as this thing goes above, it turns above 7. As I add more of this NaOH, what's going to happen is the pH is going to go up, right? As soon as I add exactly, 1 drop more than neutral, this thing will turn bright pink.
Okay.
That actually happens. In your chemistry book, it's actually, actual demonstration. It's really cool. I wish I could do this lab with you guys. It's a lot of fun. All right? And then, let's see. I'm going to mess with some of these numbers just a little bit real quick. Let's make the molarity of this acid 0.350. Oh, I can't change it. All right, whatever. All right, so what I'm going to do is I'm going to add, let's say, 15 milliliters off the bat. And I think that, all right, so I added 15 milliliters right off the bat. Got it? Now what I'm going to do is I'm going to drop in, and can you see the drops? Oh. Does it drop? Does it ever show you the drop?
No. Oh, no. Well, it's kind of like lagging.
Okay. I'm slowly dropping in, and you can notice the number up here going up.
Yeah.
I'm slowly dropping in more of this solution. Got it? And what I did, and this is literally what you do in the lab. You drop until it starts to turn purple. I'm very impatient, so I'm just pressing it lots. Right? What happens is, oh, did you see that?
Yeah.
So as I drop it, what's happening is you'll see a little hint of purple. I don't know if you can see it on your screen. You definitely can't see it on your screen. Justice, come look at mine. And for those of you online, check out this thing right here. Got it? All right. As I drop more and more of the stuff in here, do you see what's happening right there? It's turning purple, but what happens is it mixes in because that little spinny bar is mixing the liquid. That's all that thing's doing. So I'm going to slowly add, I'm not just going to click, 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 click. I'm going to add a little bit more each time. And so what I want to do is I want to get it to the point where it will just turn purple. That's it. Come on. Come on. Dude. Getting impatient again.
Yeah, there's nothing happening on my screen.
Yeah, sorry.
Oh, it's going like pinkish color to gray.
Does it? Does it switch ever so often?
Yeah.
All right. So what I'm doing is I'm slowly adding in this stuff. Because what I want to find is I want to find the point at which these things neutralize each other.
Yeah.
They balance each other out. Now what this will give me is this will be able to tell me the exact molarity of my base. Do you see how this could be advantageous inside of the real world?
Yeah.
Like this is the technique you use. You add slowly enough of this base to this. Oh, there it is. It's right there. It turned. It actually turned one click right before this, so at 18.8 milliliters. And then I clicked it once, and it turned all the way.
Okay.
18.9 milliliters. It took 18.9 milliliters exactly of NaOH to neutralize, actually to turn the liquid inside of here basic. Does that make sense?
Yeah.
Now, based off of all of that information, can we calculate out the molarity of this base? Because say we didn't know the molarity, the concentration of the sodium hydroxide that we used. This is a little bit of a different problem. But we can use the exact same techniques I just showed you to calculate out the molarity. Oh, then the molarity must, if it took exactly 18.9 milliliters of this stuff, then the molarity must have been blah, blah, blah. Does that make sense?
Yeah.
And I'm thinking, to be honest with you, I'm thinking that the molarity is going to be higher than 0.1468. Just by looking at this. Because look, it took 25 milliliters of this stuff and only 18 milliliters of this stuff. So I'm thinking the molarity over here is going to be higher. I mean, we could calculate it out very, tediously, and I don't really want to do that because I want to move on to another topic.
Yeah.
But this is literally what I would have you do, and it's actually a really fun lab.
Yeah.
Titration was actually one of my favorite stuff that we did in chemistry, and that will probably be one of the advanced labs that you'll do in college if you guys take chemistry.
Isn't it like a mandatory course in college?
Depends. Is the question that was asked of me is this a mandatory course in college? And my answer is it depends on what your major is.
Okay.
What major are you going to go into?
I don't know, engineering.
Then yes, mandatory for engineer. Nanea, what are you going to study? Are you going to go to college? I'm just curious. You don't really need to answer that, but I was just wondering. Kind of undecided. What about you, Cameron? Because I'll tell you now. That dude who wants to be a heart surgeon.
Tejas. No, Andre.
Yeah. And also the one who wants to be a...
I thought it was Tejas that wanted to
No.
be a
Andre wants to be a plastic surgeon.
Yeah, that's what it was.
Tejas wants to be a heart surgeon.
Yeah, that's what it
and Bradley wants to be an anesthesiologist,
My God.
and Maston wants to be a I don't know what he wants to be.
He's supposed to be a musician.
Maybe, I don't know. But anyway, all those guys better take chemistry, and they also all better stop screwing up their calculations.
I know he's screwing up too.
Because they're like, dude, you're gonna kill people. You realize?
the heart is a centimeter off. He's dead.
Yeah, I know. I know. Anyway, oh wait, let me just close this. I'm gonna start up. All right, so let me move on to the next topic, if that's all right with you guys. So everyone clear about how to do that kind of stuff, these kinds of problems? It really isn't anything different than what we've been doing. I promise you that. All right, let's share this thing. Let me get back up there on the whiteboard. So we talked about neutralization. We talked about acid-base titrations. Let's talk about oxidation and reduction rules. I'll be honest with you, I always screw this part up. Like, I always have trouble remembering these rules. Hey, dude, pass me that black pen right there. All right. Believe it or not, the homework for this is easy. The theory of it is easy.
Okay.
It's easy to screw it up, too. All right. Oxidation states. We have two different types of things. One is called, when we talk about moving electrons, we have these problems that are called ox redox. That's what I call it. OX redox, which stands for oxidation and reduction. I don't know what's redox. It's reduc. It's oxidation reduction reactions. That's what it's called. And I think when I was in college, I called them oxyredox. I don't know. I thought it was a cute name. All right. So there's these rules, okay? And the rules are the one of the things that I want to make sure that you know is that oxidation is when, and I don't want to screw it up, so I'm making sure I read it. Where does it say this? Is oxidation, the characteristics for oxidation reactions. Celeste, I always screw it up. What is oxidation? Oh, wait, here we go. Oxidation is gaining a proton, right?
Yeah. Proton acceptor.
Oxidation is gaining a proton. Reduction is losing a proton. How do I remember this? What is the clever way I use to remember this? Obviously, I don't. Because if I did, I wouldn't have to look it up. I think one way of remembering it is the word reduction means you've gone down in a quantity, right?
Mm-hmm.
So you have a certain quantity of electrons, and you went down in your quantity of electrons. Hence, you lost the protons. Does oxidation mean? Reduce. REDUC is short for reduction. Yeah. Oxidation doesn't mean somehow adding. I have no idea. I don't know where the word oxidation comes from. Is there a word?
Oxy.
All right. But reduction makes sense, right?
Yeah.
Reduction is totally losing electron. Oxidation, don't know. It's the opposite of losing an electron. How's that? Which means gaining an electron. There we go. I made something up. It's something cool. Got it? Now, I'll be honest with you. I think that the reason why I'm not as comfortable teaching this is because this is something you learn in chemistry in college, but I never had to use this outside of chemistry in college. And now you guys are wondering, well, why the hell are you teaching this to us then,
Yeah,
right?
exactly.
And my answer is, well, this is a chemistry course, so you need to learn that kind of stuff.
Yeah.
And maybe some of you guys might be chemistry majors or majors that are really interested in chemistry, and so this kind of stuff could be important to you. Yeah. Why am I so good at doing all of the other chemistry stuff, even though I've never used that stuff outside of chemistry? Well, it's because a lot of that stuff has to do with physics, and I'm good at physics.
Yeah.
You know, a lot of it is good at math, and I'm good at math too. But oxidation reduction, I literally don't memorize, the words or what they mean. I just look it up on tables. So there's this table that says that you assign an oxidation number. So an element is 0. Okay, so rule number 1. This is on bottom of page 171, table 4.2. You guys might want to look it up. All right? An element in its natural state is 0. So we assign these oxidation numbers to certain things. So for example, oxygen is never found, pure oxygen by itself is never found in nature. It's never found in nature because oxygen is a diatomic gas, which means what? Do you guys know? You never find one oxygen all by itself. It always comes in pairs.
Okay.
O2. Got it? So, oxygen has a oxidation number of 0. Cool? Or sodium. Sodium is a solid, and so sodium, in nature is an oxidation number of 0. Okay, what's another rule? Okay, another rule is monatomic ions have the same, the oxidation number is whatever its charge is. So monatomic ions. So for example, Na. I told you that Na had an oxidation number of 0, right? But if I'm talking about sodium ion usually has a charge of plus, right? We saw that before, right? Or if I'm talking about a chlorine ion, I usually see it as Cl minus. We cool?
Yeah.
Now, what is the oxidation number of sodium? Plus in this case. What's the charge on it?
Positive.
Positive what? Rhymes with my good friend.
1.
He's Hispanic.
Positive 1.
Juan. Yeah. The oxidation number for sodium ion is positive 1. The oxidation number for chlorine ion is
1.
negative 1.
Negative 1.
That's it. All right, rule number 3. Fluorine is negative 1. Fluorine is negative 1. Rule number 4. Oxygen is pretty much always negative 2. And hydrogen is pretty much always positive 1. Are we cool with that?
Yeah.
So write those rules down, please. I'd appreciate it. Let me show you how to apply them, because it's actually really easy. You ready? All right. So, if I have something like CO2, what are the oxidation numbers of each of these things? Okay, first thing, O2. What is the oxidation number of O?
2.
This is negative 2. Got it?
Okay.
How many O's are there?
2.
There's 2 of them. So in order to balance out those 2 negative 2's, What does the oxidation number of carbon have to be?
+2.
Nope.
Oh, +4.
+4. Because it has to, because yes, you're right. The oxygen by itself would be -2,
Okay.
but there's 2 oxygens.
Okay.
If I had carbon monoxide, though, then the oxidation number of this would be -2, and this would be +2.
Okay.
That's true. Yes, I agree with you. But I have carbon dioxide. So the oxidation number of this is -2, but the oxidation number of this is +4. You guys get it? Does this make sense?
Yeah.
Okay.
I have to go at 3:30.
Literally, really? Seriously? All right. We'll do this quick. I'll try to finish by 3:30, the whole class.
Because my bus is coming at 3:30.
SF6. Let's try that one. F is what?
6.
F is what? What's the oxidation number of F?
-1.
-1. There we go. So, if this is -1, what does the oxidation number of fluorine have to be?
+7.
It has to balance out. If I add up the oxidation numbers of each of these, they have to add up to 0.
Oh,
It's
okay.
kind of like charges, but it's a little bit different.
Okay, no, I understand now.
So there's 6 negatives. And there's only one of these sulfurs.
So it
The
has
sulfur
to be
has to have a
+6.
+6 to
Okay.
balance out with the 6 fluorines that are each -1.
Okay.
Does that make sense? You guys get it?
Yeah.
Yes? No?
He said -1.
Oh, no, I think he was answering here.
Oh, okay.
Online, do you guys get it? So what if we have 3 elements? Well, let's get to that. Let me just try one more. NO3 negative. Okay, this one's a little bit trickier. You ready? Do we have a rule for N? See these rules? Do we have a rule for N? No.
No.
Do we have a rule for oxygen? Yes.
Yeah.
-2. Oxygen is -2. Okay? Okay, check this out. This oxygen is -2. There are 3 of them. What does this nitrogen have to be in order to balance it out?
+6.
+6. I agree with you. However, there is a charge on this thing.
Yeah, it's a negative.
It's overall negative. So instead of making nitrogen +6, I'm going to make nitrogen +5. How you like them apples? Does that make sense to you?
That is.
Because this +5 will not balance out with this -6. It will leave an overall thing of -1 up there.
So if it was a positive charge instead of a negative, would it be +7?
If this were a positive charge, then
Yeah.
yes, this would have an oxidation number of +7.
Okay.
Yes, I agree with you. Because you need to have that to balance it. Got it? Okay. What happens if we have 3 numbers? Or 3 letters? And my answer is, I don't know yet. Let's see if I can figure that out. Oxidation. Here's my answer. It looks to me like none of the problems I gave you have 3 numbers. Celeste, what happens if you have 3 numbers? Like HNO3. How do I figure out the oxidation numbers on each on like a triple?
Oh crap, I don't remember that.
All right, here's what I'm thinking, okay? Now don't quote me because I probably screwed up. This is what I'm thinking. There's a rule for oxygen. Oxygen is what?
-2.
-2. There's a rule for hydrogen. Hydrogen is what?
Negative.
It's positive, and it reminds me of my Mexican friend that I had in
Oh,
California.
+1.
+1. My Mexican friend's name is Juan. I love that joke. Okay, here's what I'm thinking. If this is -2 and there's 3 of them, that's a -6 over here. There's a +1 over here. I think I need nitrogen to only be a +5 in order to balance this whole thing out to be 0.
Okay.
That's what I would do. But my answer to you, who asked, well, what happens if you have 3 elements, is I don't know. You guys got it?
Yeah.
I mean, this makes perfect sense to me. I actually think this is correct. I hate to say it, but my answer is I'm just not that good at chemistry. Give me a break. All right, let's try this one. All right. Okay, this thing is, it gets a little weird right here. All right. Oxidation reduction reactions. All right, so metallurgy is a process of producing metal from its ore. Always involves oxidation reduction reactions. The metallurgy of galena, Galena, which is known as lead sulfate, PBS. Also brought to you by viewers like you. Lead sulfate is the principal lead the principal lead containing ore. The first step is a conversion of lead sulfate to its oxide. So the first thing that we do is we roast this lead sulfate, PBS. We combine it with pure oxygen, O2. Got it? And what it yields is it actually yields PbO plus SO2. That's what happens. This is called roasting your lead sulfate, which is actually known as galena. Apparently. Got it?
Yeah.
This thing's not balanced. Help me balance this. Now you said you suck at balancing, so let's work on this. PB, there's 1 lead on each side. We're good,
Okay.
right? There are 3 oxygens on this side, but only 2 oxygens on this side.
So
You see that?
have to add 1 to 1 on this side.
It's kind of like cross multiplication.
Oh, I suck at that.
I mean, all right, here, look. It's kind of like there's no number I can multiply here in order to make it into 3 oxygens on the left side. You see what I mean?
Yeah.
So it's kind of like, well, what if I made it so that there's 6 oxygen on both sides? Why did I choose 6? Well, because this one has 3 and this one has 2, and 6 is the smallest number that I can think of that both 3 and 2 go nicely into.
Yeah.
Does that make sense?
Yeah.
So what would I have to multiply the left side in order to make it to be
By 3.
in order to make it to have 6 oxygens?
Oh, the left side.
All right, I tell you what, I don't like this idea of cross multiplication. I like using fractions. Here,
Okay.
I'll show you how. Watch, check this out. This will blow your mind. There's no number I can multiply here to make this into a 3. Because if I put a 1 here, that's 2 oxygen. If I put a 2 there, that's 4 oxygens, right? What if I put, and this might trip you out, what if I put a 3 halves here? Okay. That would be 3 oxygens.
Okay.
Because I have 3 halves of O2. Does that make sense?
Yeah.
But there's no such thing as a half or a fraction coefficient in balancing equations. So what I'm going to do is I'm going to multiply everything by 2. So I have 2 PBS. By the way, when I take 2 times 3 halves, what does that give me? The 2 cancels out with the 2, and you end up getting 3. Yields 2 PbO, PbO, plus 2 SO2. We cool with that? that was not hard balancing equations. Using those fractions are really powerful. And I don't think chemistry teachers teach you that. I think math teachers would probably teach you that. I'm more of a math teacher. Okay. The second thing, after we take this thing, is we take the pure PbO and we add carbon dioxide to it, which is a gas. And this is a solid. And what it yields is that carbon dioxide, or no, we add carbon monoxide. What happens is that carbon monoxide strips off that extra O. So we have Pb solid plus carbon dioxide gas. We cool? Does that make sense to you? So, check this out. Apparently in metallurgy, I want to have pure lead to make my car batteries. But the stuff I pulled out of the ground is not pure lead. It's lead sulfur. That's a problem.
Yeah.
So what I do is I put it in with a whole bunch of oxygen. So then that turns my lead sulfur into lead oxygen, lead monoxide. Then I take that extra lead monoxide and I combine it with carbon monoxide, and then I'm left with a byproduct of carbon dioxide and lead. Does that make sense?
Yeah.
So what goes into my factory? Lead sulfate. What do I need to bring into my factory? If I own this factory, what do I need to bring in? I need to bring in lots of oxygen, lots of carbon monoxide, and lots of lead sulfate.
Okay.
What comes out of my factory? Well, lots of lead, which I sell for lots of money.
Yeah.
But also, I have extra Pb or SO4, SO2, and also a lot of carbon dioxide. So that's probably what's coming out of the smokestacks of my factory. You see how this is actually a problem in the real world. You don't pull pure lead out of the ground. You pull this stuff out of the ground. Well, how do I get pure lead so I can use it? Through this process. Anyway, here's the question that we have is, for each reaction, identify the atoms that are oxidized and reduced, and specify the oxidizing and reducing agents. Okay, so let's go to here, and let's give me a different color pen. There's a green one right there. I don't know if that works very well. Is there a different one? There's red. Awesome. All right. What's the oxidation number of O2?
-1.
It's 0.
Oh.
Nope, it's 0. Remember, I told you. That was the first rule. Pure elements
Is 0.
are 0,
Okay.
right? When it's being used as an ion, then oxygen is often -2.
Okay.
I agree. But pure elements, 0. Got it? All right, let's see. What can I say about the oxidizing number of, let's see, how do I know S is, what is S? What's my rules for S? Okay. Sulfur is often has a charge of -2. So I'm going to say that the oxidizing number of this is -2. What is the oxidizing number of Pb then, if that's the case?
Positive
Positive
2.
2.
Positive 2.
There's only one S, one
Yeah.
Pb to balance it out. Does that make sense? Okay. Over here, oxygen has a oxidizing number of what? -2 in this case. Because it's not pure oxygen, we're talking about one oxygen.
Yeah.
The lead over here has an oxidizing number of what?
Positive 2.
Positive 2. What about the oxygen over here? That has a -2 on it, right? Right? This oxygen over here.
Yeah.
For the most part, all oxygens are going to have -2 unless it's an oxygen gas.
Yeah.
What is this sulfur? What's that going to have on it?
+2.
+4. Because oxygen is -2, but there's 2 oxygens on this thing.
Oh, okay.
So you need a +4. Does that make sense?
Yeah.
Okay. So check this out. Here's what you do. The oxidizing, oxidation states, okay, the oxidizing agent is anything that reduces, okay, it accepts electrons, okay. So the oxidizing agent, you can identify the oxidizing agent pretty easy. All you have to do is say, which one of these goes down in oxidizing number? For the lead, did the lead change in oxidizing number as I went from here to here? It went from +2 to what?
-2.
No, +2. Look.
No, it didn't change.
For the sulfur, for the oxygen, it went from 0 to what?
-2.
To -2. So that's your oxidizing agent. Oxygen. Got it? What do you think your reducing agent is? If the oxidizing agent is the one that takes the oxidizing number and goes down, the reducing agent takes the oxidizing number and goes what? Up. So sulfur, it went from -2 to what?
-2.
-2 over
to
here
+4.
to +4.
So it's PBX.
Your sulfur is your reducing agent in this case.
Okay.
You guys got it?
Yeah, I got it.
So, yeah, that's really it. That's all I wanted to show you. And they have this trick on using these numbers to balance out these equations. And I guess you can read up on that chapter. It's not really that bad after that. But I think that's, once I gave you those descriptions. Oh, we didn't do this one over here. Let's do it real quick, if that's all right with you. Because I know you got to go. And I'll just do this one real quick. Oxidizing number of this is -2. Oxidizing number of this is -2. And this is also -2. Does that make sense?
Sure.
I just went with all my oxygens. I'm doing the equation on the bottom. The lead is +2. It has to be, right?
Yes.
The carbon has to be +2 as well. This one goes to 0. Why is it 0? Because it's pure solid lead. You can tell that it's a solid because of S. It's the natural form of lead.
So it's
Pure lead, 0. This carbon, on the other hand, goes to +4. Okay. So, the one that went down in oxidation number is your oxidizing agent. Which one of these elements went down in oxidation number?
The PB.
The lead.
Yeah.
Because it went from +2 to 0.
Yeah.
Went down. What is your oxidizing agent?
Lead.
Lead. Which one is your reducing agent?
Oxygen. No.
Oxygen went from -2 all the way to -2. It didn't change. Your carbon. It went from +2 to what? +4. It went up in oxidation number, which means it's your reducing agent. You guys got it?
Yeah.
All right. I'm done, and here's what I've decided. There is not going to be any more homework from this book after you guys finish off those last 3 things that are due this week on Chapter 4.
Yeah.
I am totally done with this book. Next week, I will teach you guys something from my head. And I'm going to teach it to you in a very, I'm super excited about how fun and interesting it's going to be. And trust me, this is actually going to be fun and interesting. It's not going to be as painful as you guys have, you know. Whenever Mr. Dalday says, "Oh, that's fun and interesting," it's usually horrible. No, I actually think that this is actually a really good lesson. I'm going to teach you guys about calorimetry. And next week, what I want to do is probably have a lab on using a bomb calorimeter. We're going to make one out of a styrofoam cup.
You can do
Yeah, it's awesome. You need a styrofoam cup and a thermometer, and that's it, really. Styrofoam cup, a thermometer, and pieces of metal. And we'll make a calorimetry bomb. That's what it's called.
Does it actually like explode?
No, it doesn't explode.
Oh, shucks.
But it's actually used in actual chemistry class. And, you know, anyway.
That's so cool.
Are we cool? So next week it's going to be, I promise you it will be easier. And then your final exam, I haven't made it yet.
I thought you had an. Oh no, that was for.
I made the algebra one already.
That was for
For the final exam, I honestly am going to make it kind of like your homework.
Okay, so like a quiz.
So make sure you're good at your homework. All right?
Okay.
No, it's not multiple choice. But it's kind of going to be like your homework. All right. Anyway, get out of here. Talk to you guys later.